All right, welcome. Never mind. I was gonna crack a joke. I'm not gonna crack a joke. Okay, we're gonna continue on with 7.3, 7.4. We more or less finished with 7.1, 7.2, and 7.3 yesterday. We're in the middle of the next sheet here, and we've kind of crossed over into the math. So at the tail end of yesterday's class, okay, we started setting up what are known as equilibrium constant expressions. The equilibrium constant is capital K. Capital K has many, many subscripts. I kind of warned you about that a little bit. We will see a lot of equilibrium constants between here and the end of the school year, okay, in all different contexts. But again, mathematically speaking, they're always set up the exact same. We're always going to have our products divided by our reactants. Our products will be the chemicals or their molarities raised to the power of their coefficient divided by the same thing of the reactants, the chemical or the formula, the molarity of that stuff raised to the power of its coefficient. Okay, pretty easy math, but we'll set this up a whole bunch over the next month or so. Just in general, I don't know if I need to go too much further back, but just in general, I know I said this yesterday, but equilibrium is what? What does that mean? When I say a chemical system is at equilibrium, what is that implying? Correct. The rate of the forward and the rate of the reverse reaction are equivalent. Okay, it has nothing to do with how much, right? It's not that I have the same amount of product, the same amount of reactant. It has nothing to do with it. It has everything to do with how fast am I going in this direction versus how fast am I going in that direction. When the rate of the forward and the reverse are equal, that is equilibrium. Okay, so this math explains with a number what equilibrium means. Okay, this constant is different for every single chemical reaction out there. Okay, this isn't something we can look up in a book. This is something that is just unique to that specific reaction. So the question maybe then is, what purpose does it serve if everything's different and everything has a different value? Okay, we'll kind of get into that a little bit today. The value of the equilibrium constant, its biggest purpose, or the best use that it has, is if we know what the equilibrium constant is, we can simply use it to figure out whether or not we're actually at equilibrium. If that makes sense. So it's kind of like a reference point. It's a reference point to understand, okay, are we at equilibrium? No, we're not, because we don't have the value of K at this moment in time. So then the question is, well, if we're not at equilibrium, do we have too many products? Do we have too many reactants? Okay, that's kind of what we're going to talk about today. So let's keep going. We set this up, okay, again, products over reactants. We did one example at the end of the hour, and we used real molarities, and we plugged them in, and then we solved for the actual value of K. What is the label of the equilibrium constant? There isn't a label. It's a labelless unit. Okay? They're rare. Again, especially in science, obviously. In math class, you don't label a darn thing. Numbers are just numbers, right? You just do the math. But in science, generally speaking, if you have a number or a value, you better label it. But the equilibrium constant is a labelless value. So it just is what it is. It's more or less it's a fancy ratio, basically, between products and reactants, right? Products on top, reactants on bottom. So having said that, this is going to show up later, but I'll say it right now. If this is just a fancy ratio, products are on top, reactants are on bottom. If my value of K is bigger than 1, do I have more products or do I have more reactants? Products. If my value of K is less than 1, between 0 and 1, I should say, right? I have more reactants. We're going to use that later today. So it's a fancy ratio. It's a number that represents how much product and how much reactant we have once equilibrium has been reached. Okay. So reversible reactions are, of course, not always at equilibrium. Okay? That makes perfect sense, right? Most of the time, reactions aren't at equilibrium. So it's very common to be given some starting conditions of a reaction that aren't at equilibrium, there's a value that we can calculate for any set of molarities that are not at equilibrium as well. This is called the reaction quotient. It's given the symbol capital Q. Now, capital Q is mathematically the exact same setup as the equilibrium constant, capital K. It is literally the same math. No difference anywhere. Products over reactants. The products are raised to the power of their coefficients. The reactants in the denominator are raised to the power of their coefficients. Same, literally the same. So now what's the question? Why do we need two of them, right? If the math's the same, why is there two things showing the same math? Because our reaction is either at equilibrium, K, or not at equilibrium, Q. So we mathematically set up this ratio. We mathematically set up products versus reactants in this same mathematical setup. And then the question is, well, does that ratio equal the equilibrium constant K? If your ratio equals K, you're at equilibrium. If your ratio does not equal K, you're not at equilibrium. Okay, we'll try some problems in a second, but yes, April.
So what's the point of knowing Q?
Q can be compared to K. So K is equilibrium, Q is where you are at right now, or where the reaction's at right now.
You're looking at
Correct. Yes, correct. So it is 100% used for comparison. Q tells us where the reaction currently is. K is where it's going to end up. Because remember, equilibrium will be reached. You know what I'm saying? Like chemical reactions will naturally go towards a state of equilibrium. Yes. Okay. Unless you keep messing with it. So for example, in a chemical plant, right? If a chemical plant is producing some specific chemical for some specific purpose, okay? If they let their giant tank of mixing chemicals sit for hours and hours and hours, it'd reach equilibrium and they're not going to produce any more product that they want. But if they keep messing with it by like removing product as it gets produced, it'll never reach equilibrium and it'll just keep pushing forward, right? So there are certain ways to like prevent equilibrium when it's desirable. And you just have to mess with the conditions to make sure it doesn't actually get there. So it's, yeah, it's used in industry very, very often. Is in industry, they don't want it to reach equilibrium a lot of the time. They want to keep producing something that they can sell and make money on, right? All right. So the reaction quotient and the equilibrium constant are calculated in the exact same way. It is literally the exact same math, like I had said. So what's the difference between Q and K? If they're calculated the same, the difference is K is at equilibrium. Q is not at equilibrium. Okay? That's it. And I oftentimes transition with OK or K. Don't mind my equilibrium constant puns. Okay? Did you, or was that pity? It was pity. So then are you pitying yourself for laughing at my bad joke?
Yeah.
Okay, I got you. It all makes sense. When a chemical reaction is not at equilibrium, we solve for Q. All right, so if you're given a problem, and we will be in just a little bit, if you're given a problem and it says, the following starting conditions, right? Starting conditions or initial conditions. That's trying to imply that it's currently not at equilibrium and it's going to start heading towards equilibrium. Okay? So if you're given random molarities of all of your reactants and all of your products, and it doesn't say that you're at equilibrium, you should assume that you're not. You should assume that we're not at equilibrium, and this reaction is going to shift towards equilibrium. So always assume that when you're given molarities, we're not at equilibrium. Unless it explicitly says, these are the molarities at equilibrium. For example, okay, we ended the day yesterday with this. And it says, the following concentrations were observed at equilibrium. You know what I mean? It will be very, very, very blatant in your face. It has to tell you it is at equilibrium. If it doesn't, we assume that whatever molarities we're given are not at equilibrium. Okay, that's always our first assumption. Okay, so the exact same math. What happens is once we solve for Q, again, Q is some point in time that isn't equilibrium. We then can compare Q versus K. And from that comparison, we can figure out or solve which direction our reaction is going to head. If Q has too many products, we're going to have to shift towards the reactants to reach equilibrium. If Q has too many reactants, we're going to have to shift right towards the products to reach equilibrium. So it's a comparison. We compare the two numbers, and then we figure out, based off of where we are, Q, and where it's supposed to end up, K, which way is it going to go? So here we go. Given the following initial values of molarity for the reaction below, solve for the reaction quotient. Again, reaction quotient is the fancy name for capital Q. Capital Q is solved mathematically the exact same as we would for the equilibrium constant K. Now, the wording matters. They told us these were initial values, implying not at equilibrium. Okay, so let's set this up. Q equals products over reactants. I'm going to set it up generically first and then plug my numbers in second, just to make sure that we never forget how to set this thing up. I have, my product is the molarity of ammonia raised to the second power because of its coefficient of 2, divided by the molarity of nitrogen to the first power and the molarity of hydrogen raised to the third power because of its coefficient of 3. I will then plug my numbers in. I was given an initial molarity of ammonia equal to 1.0 times 10 to the negative 3 divided by, oh, I'm sorry, that's squared, my bad. Divided by the molarity of nitrogen, 1.0 times 10 to the negative 5 molar, first power, and then hydrogen, and I solve for Q. I should have shifted this over a little bit, that's okay. What do you get for a value of Q? What is the reaction quotient from that setup? I suppose 2 sig figs is where we should keep it because everything else is in 2. If you went to 3, that's cool. I mean, it is what it is. Okay. Sorry. What'd you get?
I don't know. What did you get? It does not seem right.
Yeah, I'm getting that.
Yeah, I don't know how to plug
Make sure, yeah, and when you're taking things to a certain power, right? Again, you want to make sure that you're only taking that one specific chunk, that power. So like, if you follow along with the way I would enter it, Jake, I punch in 1.0 times 10 to the negative 3 squared, hit enter. I then I hit divided by, and it'll say like ANS or answer divided by, right? Then I'll punch in 1.5 or 1.0 times 10 to the negative 5, hit enter. And then I will divide by parentheses 2.0 times 10 to the negative third, caret 3, close parentheses, and hit enter.
Oh, I got it.
Okay.
I was multiplying the two bottom ones, not dividing.
Yeah, and when you do it piece by piece by piece, right? Anything in the numerator you multiply, anything in the denominator you divide. So yes, that's a common mistake too, is that you end up accidentally multiplying by this when you don't need to. You can't get it in a little bit here, Jake. Well, I'll help you out. Anyway, so we have Q and K now. Later, they tell us that the equilibrium constant for this reaction is 6.0 times 10 to the negative 2. We just solved for Q equaling 1.3 times 10 to the positive 7. Okay. The idea here is this represents the ratio of where we currently are. This represents the ratio of equilibrium, where it's going to go. Remember, equilibrium is kind of like the end goal. That's where this reaction is going to shift towards. Reactions will naturally, spontaneously approach their equilibrium. So, we make a comparison. Now, I strongly recommend when you make a comparison between K, equilibrium, and Q, not equilibrium, you do it in alphabetical order. Here's what I mean. In the alphabet, K comes before Q, yes? Excellent. So I'm going to say that in this instance, K is less than Q. Right? It is. The inequality points in the direction my reaction is going to shift. So my less than right here is like pointing left, right? My reaction as a result is shifting from the products towards the reactants. Okay? If you set up your inequality in alphabetical order, you don't really have to think. But for the sake of argument, let's think. This is a ratio, right? It's a ratio of products divided by reactants. This number is very, very large. The equilibrium value is very, very small. Okay, 0.06, right? So at equilibrium, according to this value, we should have way more reactants than we do products. Because it's a ratio, right? When the ratio is bigger than 1, that means the numerator is larger than the denominator. We have more products than reactants. When the ratio is less than 1, it's implying that our denominator is bigger than our numerator. We have more reactants. So currently, we have a very, very large value of Q, meaning we have way too many products, and at equilibrium, we should have way more reactants than products. So long story short, where we are, we have too many products. That number is bigger than 1, way bigger than 1, and it's supposed to be this. If we have too many products, we must have to shift left to make more reactant and use that product out. Okay, that's how you think about it, right? But again, you can take the thinking out of it by just setting up your inequality in alphabetical order. Make sense? Okay. K is greater than Q, you shift towards products. If K is less than Q, you shift towards reactants. And if K is equal to Q, you're at equilibrium. Makes sense? K is equilibrium. If you're not sure and you solve that math, and it's like, oh, it does equal K. well, then there's no shift to be had. It's where it's supposed to be. It's good. Okay. Here's how they have set it up. This is from the textbook. Again, they are setting up their inequalities the opposite way, because in reality, again, K is the destination, Q is where you're at. So putting it in this order makes sense from like that perspective. This is where I am, that's where I want to go. This is where I am, that's where I want to go. And when I say I am, I should really be more specific, right? This is where the reaction currently exists at in its ratio. This is where it's supposed to be at equilibrium. So long story short, K and Q, or Q I should say, is always going to shift towards K. Q is, it wants to equal K. The reaction wants to be at equilibrium. The reaction will always proceed towards equilibrium. So when our Q does not have enough products, we need to make more. When our Q has too many products or not enough reactants, we need to use that product up to produce more reactants. The end goal is always to reach equilibrium. All right, let's sprinkle some more fun in. We are now going to be talking about gases and gas equilibria, equilibria being the plural of equilibrium. Okay. In all of the examples up to this point, we've been using molarity to describe reversible reactions. However, we can also use partial pressures to describe reversible reactions using gas. The only difference here is instead of having brackets representing molarity, we have capital P with a subscript of the chemical name, which represents a partial pressure. Capital P is pressure. The little subscript behind the capital P tells you what substance you're looking at, right? If I have capital P, O2, that's the partial pressure of oxygen. If I have capital P, CH4, that's the partial pressure of methane. Okay? So you can set up the math for an equilibrium constant using pressure. You can set up the math for the reaction quotient using pressure. So these are given the subscript little p, or big capital P, I guess. Kp or Qp. Same math, partial pressures instead of molarities. Same setup, partial pressures instead of molarities. So really, it's the same darn thing. What's that? Yeah, kind of. And we're just using different values. When you set it up generically, you don't want to use brackets, right? Brackets is implying molarity. So you'll notice how I have just good old standard parentheses going on. Do weird things today. Anyway, so the math is the same. We're just simply swapping out molarities for partial pressures. All right, here's a gas one. Given the following partial pressures, solve for the equilibrium constant of the reaction below. So they're giving you partial pressures and they want you to solve for the equilibrium constant and there's nothing else given. We can kind of assume that these must be equilibrium partial pressures. You know what I'm saying? Because they would have to give us more if the pressures they gave us weren't at equilibrium. If they're trying to say that these pressures are at some other point in time not at equilibrium, and they want us to solve for the equilibrium constant, well then we're going to need more information. Not possible, unless these are at equilibrium. So they must be. Go ahead, set it up. I think you can do it. You don't need me. That's the setup. Again, we're using just different symbols for our generic setup, but the math's always the same. Products over reactants, raise your products to the coefficient, raise your reactants to the coefficient. I plug in my real numbers. I have and what do we get for a value of K? $1,900? Is there a second on that?
Yeah, 1920. I got one. I got 19. Oh, same page, yeah.
I don't know what I'm doing wrong.
Oh, syntax. Very good. Yeah, I'm getting 1,900 or 1.9 times 10 to the 3.
Oh, I got it
Oh, good.
right. Milestone.
So this is K. That's the equilibrium constant using partial pressures. Now, the second part here is asking something slightly different. The second part is asking, what is the total pressure in the reaction chamber at equilibrium? You get it? 19.2 or 1920? Then one of your things is off. No, I'm saying you're off by a factor of 10-ish, right? So your scientific notation things must have been entered incorrectly. Either this or that got punched in wrong.
Bring the five.
Let me see it.
It's still working. I don't
It
know.
was power side, oh, mine has that. Wait, if you, it's still working.
I know. I mean, there's a battery.
You're gonna have to play with it, figure it out.
What this does.
Oh,
All right, so this bottom chunk, I apologize for the time lapse there on the video. The bottom chunk here is an equation from your formula packet. On the second page of formulas, we have gases, liquids, and solutions section. The third equation down is saying that the pressure total equals the partial pressure of the first gas plus the partial pressure of the second gas plus the partial pressure of the third gas, and so on and so on and so on and so on if you have more. So all we need to do to get the total pressure here for the second half of this problem is add up all the partial pressures of all the pieces. That's easy. The total pressure should equal the partial pressure of NaCl plus the partial pressure of NO plus the partial pressure of Cl2. So 1.2 plus 5 times 10 to the negative 2 plus 3 times 10 to the negative 1. And what do you get? I suppose it's 1.55 actually, isn't it? Yeah. Okay. Cool.
I'm aware.
You're so happy that you got.
Little victories.
Okay.
Sorry.
Struggle. Why would I do that to be little? Unbelievable.
No wonder you got written up earlier today.
Hey.
You got written up.
Sorry, touchy
Why
subject.
Oh, yeah.
Touchy subject, I'm sorry. I apologize. Let's do this. Sorry. I'm not a nice person sometimes. Given the following initial partial pressures for the reaction below, solve for the reaction quotient. Now, it's telling you to solve for Q. That's the first half of this. You know how to set that up. That's the same as the other setup, same as K. But when you solve for Q now, we're going to compare it to K, and then it's asking which way we're going to shift. Go for it. I don't think you need me. Try this, please. Unless you need a snarky comment, I don't know if I'm your guy.
Equal to. I miss water. I didn't do it for today. What?
I am a little confused, but I don't fully see what he does.
Yeah.
Okay.
Thank you so much.
I have a hunch. Both of them Tyler, you know.
That'll do it. I'll get you to
I haven't had that.
See, that'll do it. Unprovoked.
I'm reading between the lines, but I doubt that.
What'd you say?
You don't understand basic concepts of life. I don't know, like.
I'm asking how you were.
That never happened. I thought it was like.
Not today. It was a while ago.
Do you remember?
I don't know if it happened. That sounds funny.
Do you? Was it in class?
Oh, yeah.
You're just mad that I beat you.
Oh,
In Greenlit.
oh.
I have to fight with Sorry.
You're good. I want to take this class. It sounds like a good time.
It's so fun.
It's great.
Which is unbelievable, because literally on the surface, like, British literature sounds like
Oh.
quite literally.
Lots and lots of teaching.
No, correct. And I've very much gathered that. I've heard that from so many students over the years.
That's the only reason this class is variable. It's because you're
Thank you.
teaching.
Oh,
But I've heard, like, you know, so many positive things about that class. And I'm like, oh my gosh, that sounds like my worst nightmare of a class. Like, British literature just sounds so far from what I'm interested in.
I think it's like reading Shakespeare. you're shy, you literally, if that, I'm not a shy person. If you're shy, don't like your phone you literally.
You got that?
Yep.
Excellent. Now, this is Q. That's K. We make a comparison. This is where the reaction currently is. This is where the reaction is going to go. Remember, reactions will reach or approach equilibrium. So, if I make a comparison, I'm going to do it in alphabetical order to make my life easier and keep the thinking to a minimum. K, in this case, is greater than Q. This is like 2,000, right? That's 0.4. So Q currently is smaller than K, or K is bigger than Q, however you want to say that. Meaning, we need more products. We're going to have to shift to the right. So again, the whole point of this, or the whole purpose of these comparisons, is to figure out, okay, where are you, or where is the reaction, and where is it trying to go? Do we currently have too many products, not enough products? And you make a comparison, and then you decide which direction you're going to head. Do I have one more?
Yeah.
Sweet. A little different. Given the following data, solve for the partial pressure of NO2 at equilibrium. The partial pressure of N2O4 at equilibrium is 2.71 atmospheres. You have all the information you need. It's just a slightly different problem. Go for it. I'll let you think. April was done with this 5 minutes.
Erase it all.
Good.
And I cried. I was so scared. It was my second grade school. As a freshman, and I got yelled at for it.
He does.
Like, better listen to the whole. That was the worst part of the whole thing.
I don't remember that being part of the class.
I swear, small group was the most stressful thing, because if he said a number of homework and you did not turn the page, it's blank, you're like.
Because then you work your whole homework, like, it's not completed. It's like missing problems.
Because there was no reminders. of what
That's some brutal.
Good luck. That sets you up for life later.
it's gonna be after you-
Wait, hold up.
Just because I did doesn't mean I didn't.
make sense.
I almost have something. Sorry for that.
No problem at all. You're trying. That's exactly what I want. Thanks for stopping me.
I knew it.
This is way more powerful than you just calling forward. Thank you. Stop me. I'll stop.
I just heard
Yeah, I've seen close to this. Math and science are not good. Now it's just L's, right? 1.33 equals x squared over 2.71. Right? So I can multiply both sides by 2.71. I'll show all the intermediates, I guess, just for fun. And I get over on the left-hand side 0.36043. This equals my x squared. So now, I square root that, and I get a partial pressure of NO2 equal to 0.600 atmospheres. So slightly different twist, but again, we had all the pieces we needed. We just needed to set it up and kind of analyze it. We got 10 minutes left. You can start working on homework topic 1 if you'd like. Some of the early stuff on that assignment is this stuff. So we'll call it a day right there. People online, thank you very much for joining. I appreciate your attendance.